I'd just like to start by acknowledging that we're meeting on the unceded lands of the Ngunnawal and Ngambri people and to pay our respects to elders past, present and emerging. So today we're very lucky to have Ron Hackey. So Ron is director of the Australia-New Zealand IODP consortium, and he's been with us in that role since 2022. Going back further in time, 25 years or so, he did his PhD at the University of Western Australia, was then a junior professor at the University of Kiel for a number of years, and then spent 10 years or so at Geoscience Australia, including in the role of director of onshore seismic magnetometers. Yeah, take it away, Ron.
Thank you, Adele. Good afternoon, everyone. Thanks for coming along and signing in. If we've got people online, are there people online?
Yes.
Yep, cool. I'm going to try and use the mouse here to do all the pointing, so I'm going to sort of stand here. Look, it's great to have the chance to give you a presentation, hopefully not the last, about this grand finale. First for me, but a grand finale, this IODP Expedition 405, which was tracking tsunamigenic slip across the Japan Trench. And for me, it's kind of an opportunity to test an idea that I started developing with a colleague in Chile about 15 years ago. And we never quite finished it off, and this is kind of the incentive to do it. And mixed success so far in terms of finding time to do all of that. But before I go too much further, this grand finale, it's only a grand finale because it's the last expedition under IODP, this International Ocean Discovery Program. So the current or the previous version of this international collaboration in scientific drilling actually ended in September last year during the expedition. But look, I don't think it's the end of this scientific drilling initiative. So you can see here that the history of scientific drilling goes back almost 6 decades. And there's been hundreds of holes drilled around the world into various parts of the oceans. And it will continue to keep going, as is the nature of the world today. It's going to happen in sort of a more fragmented sense. But we know that the Europeans and the Japanese have teamed up, and they're running this International Ocean Drilling Program, same acronym again. And China is emerging with a drilling program, and the US has got intentions, but let's see what happens in the US. But basically, I guess the message here is that this was the final expedition under this IODP, and then but there will still be more stuff happening. The context for this expedition was the 11th of March Tōhoku-oki giant earthquake off the east coast of Japan in 2011. It's one of the largest earthquakes ever recorded, so magnitude 9 or 9.1, I think. And what was really unusual about that earthquake is the slip on the fault plane on that subduction interface came very, very shallow all the way to the trench, so where the subducting plate meets the overriding plate. And that was the main reason for the very extreme tsunami that hit the coast of Japan off there, that sort of unexpected magnitude of that tsunami. So, depending how you measure it, the slip there reached maybe 50, 60, 70 meters maximum on that earthquake fault when that earthquake happened. So there's different ways to do it with the crustal deformation from GPS, seafloor geodesy. Japan has great networks for that offshore as well. From the earthquake parameters, you can get pretty high slip all the way shallow to the trench, or using the tsunami run-up sort of style of work as well. So what's very clear is there's a lot of slip, 50, 60, 70 meters, which is a lot moving on an earthquake in a few minutes. It was very, very shallow, close to the trench, which meant there was a lot of displacement of the seafloor, which was the reason why we got the big tsunami. So it's unusual if you think of it in the sense of what controls these, what are the sort of the understanding of what controls these giant subduction zone earthquakes. So the seismicity is really controlled by the frictional state of the plate interface. And the sort of, I guess, the common or the classic idea is you've got these regions that are seismic, they're unstable. So it might be the locked parts of the fault that for hundreds of years or decades, they stay locked and the stress builds up. And eventually it gets to the threshold, the stress releases, the fault plane moves, and you have an earthquake. You also have areas which are referred to as conditionally stable. So they generally slide freely. But at times, if they're triggered by something adjacent to them, the slip can then move rapidly through those parts of the fault as well. And there are other parts which are sort of generally considered aseismic. They're stable, they never lock, so they never sort of have that ability to build up the stress, and they sort of freely sliding past each other. And you can see in this image here, that typically is thought to be in the shallowest parts of the plate interface. And so that's where we expect, we don't expect to have rapid slip, seismic slip in that part of the system. Yeah, so, but the Tōhoku earthquake was obviously different. It did happen. And the question is, why did that happen? So to understand why, part of this is it helps have some materials from the fault zone. And these fault zones tend to be hundreds, thousands of meters below, or thousands of meters below the sea surface. And that's where something like IODP comes in, where you can then have that capability to collect the samples. So the site where this expedition went to last year was actually drilled in 2012, very rapidly, right after the earthquake, a year or so after the earthquake, which was quite an impressive turnaround to get an expedition like that planned within a year of the earthquake. And samples from the fault material obtained during that expedition showed that the material in the fault zone was dominated by really weak smectite clays. And so that had very low shear stress, which means it can move very easily, deform very easily, and it can accommodate a lot of slip very quickly during the earthquake. It also showed that the stress built up over the many decades leading, or hundreds of years even leading up to that earthquake, was completely released. So all that stress disappeared. And there's also evidence from frictional heating that the earthquake, from the borehole temperature data that were put down into the borehole, that also indicated it's very low friction on that fault interface. So that was some of the key characteristics of that fault zone. There was a sort of a piece of core here collected from the fault zone. You can see in this image here, left is the top, right is the bottom. And you can see a whole bunch of things in there that we don't really have time to go into too much detail. This dark brown scaly fabric clay, which we got cored through this again in the expedition, looks a lot like chocolate. Sure, it didn't taste as good. But then there's a particularly sharp contact in here, which is basically considered as the fault plane. So that's where everything slipped, right on that fault. So in that expedition, it was really shown that this smectite clay was really the critical unit. So you can see a map here, this JFAST site, which is the same site that was visited on the expedition last year, just on the landward side of the trench. So drilling through the accretionary prism, adjacent to the subducting incoming plate, which is highly fractured with these bend-related faults. And in this drill section here, you can see the lighter grey areas are where there was no core collected. The darker grey areas are where there was core. This Unit 4 sheared clay is where that smectite-rich clay was dominant. And there was also an equivalent layer in this older DSDP, Deep Sea Drilling Program site, which was, I forgot what year it was. It was probably the 70s or the early 80s or something like that, probably the 70s. Yeah, so the next slide here, this sort of shows I guess, the clay content in the rocks that was sampled in that, through the accretionary wedge and into the fault plane down here. Very high smectite content. And that's sort of believed to be the reason why that slip was so easily accommodated during that earthquake. And there's an equivalent layer on the incoming plate at that DSDP site 436, where you also have quite a predominance of smectite in a 5 meter sort of thick layer in that incoming sediment. So that's the layer that then becomes the fault plane as all those sediments are shoved into the subduction zone. So Expedition 405, that one that I had the fortune to go on last year, referred to as J-Track. So the idea was to go back to that same site. This JTCT01A is the site that's in the accretionary prism, or through the accretionary prism, and to return to that site and get more samples and to see whether that fault is, whether the stress is starting to build up again. Is the fault stuck again? Has there been deformation since? And still very early days, but there were some indications that a borehole that was drilled last time and was cased because they put sensors down it might have even been bent. So there's possibly been some deformation happening, but that's got a bit more of a way to go yet. So then the idea was to drill a second hole on the incoming plate to look at the nature of those sediments directly in front of where that high slip region is. So there's a seismic section here you can see at the top, and then an interpretation down the bottom. The plate interface here of the subducting plate is quite rough. There's a lot of bend faulting, normal faulting as that plate bends and goes into the subduction zone. So the main side was drilling through the accretionary prism into one of these horse blocks through some of the sediments that are covering the incoming plate. And then another site, the one further out, is sampling those undisturbed, undeformed sediments on the plate as it's coming into the subduction zone. What's really impressive here is the things that are done here. We're thinking here we're in 7,000 meters of water, and we're drilling another 900 meters into the seafloor. And I find that quite phenomenal, that the technology that goes into that. And I'll touch more on that as I go through as well. So the objectives of this expedition were really about characterizing the geological composition and the structure of the frontal prism, the décollement, the fault zone, and the subducted oceanic crust that's below it. Characterizing the stress state within and around that fault zone that experienced the large co-seismic slip, and also characterizing the hydrogeology of the plate boundary fault zone. So how are fluids moving around in the fault zone and in the frontal parts of the accretionary prism. So how do we get those samples from the fault zone? Well, in this case, it was this dedicated scientific drilling vessel, Chikyu, which has been operated by Japan since about 2005. So Chikyu departed on the 6th of September last year to start this expedition, and we came back on the 20th of December. There were two parties. I didn't spend the whole time out there, but that was 4 months or so of drilling out on over the Japan Trench. So Chikyu is big. There's a nice model of Chikyu here if you want to have a closer look. 210-meter long ship, which means even in rough weather, it's just a gentle rocking, which is conducive to sleep, I would say. It's got this derrick, which I guess accommodates all the instruments and the engineering to get the drill pipe down through the ocean and into the seafloor, and it's about 130 meters up above the seafloor. You could outrun it on your bike if you were riding along, because it's big and slow and cumbersome, but an amazing piece of engineering. And I've just got a few little snapshots here of that engineering. It's really hard to explain, but there's basically this photo here is looking upwards into that derrick. On the side here, you can sort of see some cylindrical looking things. That's the drill pipe. So there's 40-meter segments of drill pipe. And if you're going down 7,000 meters, you can do the maths of how many of these 40-meter segments you need. There's basically robotics that take a piece of that drill pipe, put it over, screw it into the one before, lower it down, get another one, bring it over, screw it in, lower it down. And that process in 7,000 meters of water took about 40 hours to put the whole string down, and then 40 hours to bring it all back up again when you're finished. So you can imagine that takes a fair bit of time if there's a problem, and think, okay, let's get everything back and start again. So, okay, you've got 2 days off while everything is redone. Never you've got 2 days off. There's always more to do. But the engineering here is incredible, because of course the whole time you've got this drill string down into the seafloor, and the ship is moving up and down. So there's all sorts of mechanisms to try and accommodate that motion on the ship as well. But ultimately, what it comes down to is there's a drill bit at the end of this string of pipes. It's about this sort of diameter, and it goes round and round, and you can see there's a hollow in the middle. So it basically carves out a pillar of rock that's left behind inside the drill string. That's brought back up to the surface, and then the drill is extracted. Sometimes things go well, sometimes things don't go so well. So here's a picture of one of the drill bits after we tried to go through chert. So chert is not very easy to drill through, and it should have looked like this, but we came back up after a while when the engineers were saying, this is not going anywhere. You're just going around in circles. So everything was just smashed up in the bottom of the borehole. So that's one of those cases where, okay, we better bring everything back up, check the drill bit, and then start again. And it became pretty clear what the problem was. So the whole process there is about getting cores. And the core process starts, like I said, you drill that pillar of rock. It gets put inside I guess a plastic piece of cylinder. I've got a little piece here that you can have a look at afterwards as well. You can see a photo here where they're pulling the plastic lined core out of the metal core barrel, which gets lowered on a cable down to the seafloor and into the rocks. That process took several hours to go down, and then another couple of hours to come back up. So then that's all done in 9.5 meter segments. So there's a 9.5 piece of perspex like this with the rock inside it. It's brought up. They start looking at the cores on the deck. Hopefully you don't get an empty core barrel like this one. So there's nothing in there. Hopefully you get something more like this. And here you can see some oceanic crust basalt sitting inside the core liner. So those 9.5 meter segments that come up from the drill hole are cut into 1.5 meter segments. They're set aside, and then they're X-ray CT scanned. Then they're split in half. Half is archived for posterity, so they're kept in an archive form forever. The other half is the working half. So then people start looking at the core and start flagging, I want a sample there, I want a sample there. There's lots of discussions about, okay, well, how are we going to handle it when multiple people want samples in one spot? And then the sampling process goes ahead. And people like myself had the job of making sometimes these little cubes for measuring physical properties and things of the rock. So you can see PMAG for paleomag, impedance measurements, so electrical impedance measurements, P-wave velocities and all that kind of thing. So that's a quick overview of how the coring process sort of works. On this expedition, I'll just run you quickly through the process of what happened. So the first part of it was going back to the drill hole from 2012 and retrieving and reinstalling a string of temperature sensors in that hole. Then there was a period of logging while drilling. So that's measuring the physical properties of the surrounds of the borehole using various instruments in the actual borehole. That was done at both sites. And then there was the coring operations. So the first one was coring down to the sort of, I guess, the bottom of the accretionary wedge. There was a second drilling effort to go through the fault zone. And then it was some shallower drilling. Well, actually, this is then on the incoming plate site. So drill down to the base of those sediments to the top of the oceanic plate again. And some shallow piston coring near the surface to get some high resolution, nice undisturbed samples from near the surface. Go back and do that on the plate over the accretionary wedge. And then the very last coring hole was drill all the way down, not core all the way, but just do that drilling through the plate boundary into the basalts of the subducting plate. And that took a couple of attempts until we got there. And then the last step was a new borehole in that same region with temperature sensors down the hole. And that was to complement the other hole. So there's basically two holes there now with temperature sensors. I'll touch again on that in a moment. So what happens then? This is a map. You can see the scale here, about 100 meters. There's a whole bunch of holes at that site now, going back to the previous expedition, which is sort of the lighter colored ones. And then there's a whole bunch of other holes down there that were drilled during this expedition. So 11 holes, 2 of them were the observatory, 2 were for the logging while drilling. There were 6 coring holes, 126 cores were collected of varying lengths, but they're no more than 1.5 meters. There's a core recovery rate of about 55%. So of all that attempts to core, you only get about half of it back. And then the deepest core was 956 meters below the seafloor, taking into account the sort of ocean depth. That's 7,837 meters below sea level. So yeah, pretty deep, pretty amazing. On the incoming site, there were 5 holes, 1 for drilling, 1 for logging while drilling, 4 coring sites, 45 cores. The deepest core there was only 290 meters, but again, it's in 6,500 meters of water. So I can only give you a really brief summary. I'm going to hide behind the fact that this expedition is the data and the results are still under moratorium and just waiting for a paper to come out, and then the expedition report will be published, and then I'd be able to say a whole lot more, but that hasn't happened yet. But basically, we've got cores from the accretionary prism, the plate boundary fault zone, and those igneous rocks of the incoming subducting plate. And there's lots of data. People took thousands of samples to do all their geochemistry, their friction measurements on samples, and all that kind of thing. And then there were 128 sensors, temperature sensors put into that new borehole. Those sensors can measure to 1,000th of a degree. And the combination of the temperature data from that hole and the other hole means it'll be possible to have make some estimates of how the fluids in that system are moving around, the path they're moving, how fast they're moving between those different boreholes, and that will give us some ideas about the fluid movement along that plate boundary fault. Okay, so I probably should tell you a little bit about why I was there. And I think when we're looking at these kind of things, we're always thinking about how we're translating the science that we do into that societal benefit. And I think for an expedition like this, it's pretty obvious. We really want to do something that's going to help mitigate the risks of these subduction zone earthquakes and the tsunamis that result from them. We often ask the question, can we predict when an earthquake and a tsunami will happen? The answer to that is probably pretty difficult, probably not. But maybe we can do a little bit more in terms of predicting or forecasting if an earthquake happens, how big is that tsunami going to be? And I'll run that scenario by you. And this was the sort of the thinking behind the science I'm doing here and this idea I had with the colleague in Chile a long time ago. So 2 scenarios I'll present here. The first one here, these scenarios are kind of driven by a conversation I had with Dan Jackson, who was the head of the Tsunami Warning Center at GA around the time of the earthquake. And he commented to me, the earthquake happened, we do our models of what the tsunami might be. And we assumed that the earthquake would have a really big extent because of the amount of energy that was released. We expected it would have a huge rupture zone along the Japan Trench there. And he said, we're wrong. And why were we wrong? And then I sort of had a look at it and thought, okay, we had our results, which I'll show you in a minute. If you'd asked me, I would have said to you, no, the earthquake, if it happens here, will only have this kind of extent. And like I said, I'll show you why. But there's obviously a very big difference between those two scenarios in terms of the amount of slip for a fixed amount of energy released during the earthquake, and then the tsunami that can be generated by it, and how much of the coastline could be affected by that. So if we do some really simple sort of calculations here, we think of seismic moment, which is a measure of the size of the earthquake or the amount of energy that's released. And we can say that seismic moment is a function of the shear modulus on that fault plane, the area of the rupture, and then the amount of slip. And we can flip that a little bit around. Say the slip is the seismic moment divided by the shear modulus times the area. So let's think of a couple of scenarios here. We've got a width of the subduction zone of about 200 kilometers. We've got the moment. This is sort of roughly the moment that was calculated to be released. A lot of the assumptions, that's the seismic moment release. This is the shear modulus we assume for that. Two rupture scenarios, 800 kilometers ruptures, so the entire length of that sort of fault segment, or maybe only half of it, which is sort of what we ended up seeing. And if you do the simple maths there, for this really extensive earthquake, for the same amount of energy, the slip is only about 30 meters. But if it's in a smaller area, that energy is sort of concentrated in a smaller area, and you can have more slip. More slip, you can have more displacement on the seafloor, you can have a bigger tsunami. So it's a very different tsunami scenario. So if we could find a way to sort of have some kind of insight into, when an earthquake happens, how much of it's going to rupture, I think that would probably be a pretty good thing. So I think I've already said this, the rupture extent constrains the amount of slip. The amount of slip constrains the seafloor displacement, and the rupture extent and the seafloor displacement constrain our models of the tsunami that might result from that. So this sort of led to this little hypothesis here that subduction zone flexural rigidity, I'm going to come to that in a moment, could be a proxy for the maximum likely extent of slip during a giant earthquake. And I'll show you why I think that. And now I've got to make a little bit of a diversion here and talk about flexural rigidity. So the lithosphere we know has strength. It can support loads. So if we put a mountain range or a volcano onto the lithosphere, it was supported in varying ways depending how strong that lithosphere is. So if the lithosphere is strong, we could think of it as a rigid elastic plate. You can think of the table with the bottle of water sitting on it. The table can take it, nothing happens to the table. If it's weak, you've either got a flexible elastic plate or maybe it's just completely weak. In the other extreme, you can think of an iceberg floating in water. There's a root to that iceberg in the water. There's, what is it? 80% is underwater and only 90% underwater, 10% on top, whatever it is. So when you map out this flexural rigidity around the world, you'll generally see, and there's a map here that I computed with Andres Tassara, this is the guy in Chile, a map of flexural rigidity around of South America. You can see that flexural rigidity is high in the sort of the old cold continental interior. And in the oceans, which tend to, parts of them are warmer, it can be young and more flexible. It'll bend more easily, so it's weaker or a low flexural rigidity. How do we compute that? Well, let's just have a look at a really simple equation here. This is a sort of a classic equation here, where there's a restoring force. So that's reflecting the strength of that elastic plate. So if you put a load on it, how does it resist that load? A buoyancy force. So again, the crust or the lithosphere is buoyant in the asthenosphere. What's that buoyancy force propping everything up? And those two things balance the weight of the load that you put on the top. And then basically there's this D parameter here is the flexural rigidity, which is a function of Young's modulus, Poisson's ratio, and this parameter called effective elastic thickness, which is a measure of the thickness of that elastic plate that you're putting the load onto. One way we can estimate that is to look at the, well, hang on, I'll talk a little bit just to sort of demonstrate here. This is just an example of, a load, which might just be topography. It's, loaded onto some kind of elastic plate. If everything's weak, so an elastic thickness of 0, then you just get classic airy style isostasy, like an iceberg. So you get a thick crustal root where you've got the highest topography. If you've got some strength, then that topography can be a little bit more extreme in a way, like it's sort of shown here. And the moho down beneath compensating it may not be quite as deep, and it'll be a bit smoother because there's some strength to the lithosphere that's helping to support that load. In the extreme, things would just stay like this. So if you had infinite strength in the lithosphere, all the loads would just sit on top and nothing would happen. So yeah, like I said, weak, the load is compensated isostatically with sort of local isostasy. Think the iceberg, and an infinitely strong is like the bottle on the table. And then in between, there's the example, maybe put your bottle on a waterbed or something like that. Not that anybody's got waterbeds these days, I don't think. So yeah, and we can estimate that flexural rigidity by looking at correlations between gravity anomalies and topography. So here again is an example where you have the lithosphere, you put some loads on it or under it. So it might be some magmatic underplating or something, and then, or topography, which could be a mountain range or volcanoes or whatever. In the extreme case, again, where you have a zero elastic thickness, so airy type isostasy, the Bouguer gravity anomaly will correlate with the topography. So where you have topography, you'll see a gravity anomaly. In the other extreme, if the plate is infinitely rigid, you'll see no correlation between Bouguer gravity and topography. So there's topography here, but there's no gravity anomaly. So we can basically have all sorts of fancy methods, which I'm not going to go into today, and I never completely understand them properly, to work out what this flexural rigidity might be. And that's how we come up with a map like this of South America, and people have done it endlessly all around the world in different parts of the world. And so the question is then, what about flexural rigidity and subduction zones? So when we made this map, we looked in this region down here, which happens to be the home of the world's largest known earthquake, the magnitude 9.5 Valdivia earthquake from 1960. And it seems to correspond nicely with a low area of low flexural rigidity. So this is not a great map because I've never had the chance to remake it yet. But what we see here is that slip during that 1960 earthquake initiated in a region where you've got quite high flexural rigidity. So that's the blue colors. So that's where it's supposedly strong lithosphere. So it initiated here, and then it propagated through a region of low flexural rigidity, which is the red colors. So it started here and propagated south here by about 1,000 kilometers. Okay. So that's kind of the observation we made, and that sort of leads to this hypothesis. If we see that kind of behavior elsewhere, could we have an indication that if an earthquake happens triggers in a certain part of the plate interface, we can estimate reasonably quickly what the energy release is. What can we say about the extent of that rupture and then potential tsunami that results from that? So we've looked at all the ones around the world. We've computed this flexural rigidity for most of the sort of the trenches around the world, and then I'll show you quickly. I'll run through each of these sort of magnitude 9 and above earthquakes to see how it looks. So the observation is, when we look at that, with one exception, this kind of sort of observation works. So they tend to initiate in regions of or near or a transition from high to low rigidity and propagate through regions of low rigidity. Of course, there's always one exception. So we've seen the Chile one, that seems to work pretty well. The 1952 Kamchatka earthquake, again, you can see rupture initiated up here and propagated through a patch of low flexural rigidity. And I haven't looked in detail, but I think the recent earthquake in this part of the world had almost the same sort of behavior. Like I said, I haven't plotted that on a map yet either. This 1957 earthquake in the Aleutians Trench, maybe it didn't initiate in a region of high flexural rigidity. That white line's not so obvious, but the rupture was limited to this region of low flexural rigidity. And when it reached that sort of high fore-arc flexural rigidity, the rupture didn't propagate much further. The Alaska earthquake, again, it's maybe not so clear, but it initiated in a region of high flexural rigidity and propagated out into this region of low flexural rigidity. So that seems to work. Here's our exception. The Sumatra earthquake, completely the opposite. Started in a region here, and you might have thought, okay, by this hypothesis that the rupture should have gone this way. But no, it went the other way, and it went right through a region of high flexural rigidity. And this is part of the reason why we got to this point 15 years ago and said, oh, hang on, how do we explain this? The Japan earthquake in 2011 seems to fit really nicely as well. So rupture initiated here, and the dominant slip was through this patch of low flexural rigidity. So that's kind of the observation with that one exception that start in high flexural rigidity, propagate through low flexural rigidity. At the time, the best model we came up with was we came up with this sort of simple model. Here's the trench, here's the subducting plate coming down underneath the fore-arc, and you have these patches on that subduction interface which are frictionally unstable. So they're the ones where stress can build up, and eventually it reaches a threshold and that patch breaks, and then the rupture will potentially propagate much further. And this is one of these regions where you have the conditionally stable region where once it's triggered, it'll start rupturing. And if it's the right kind of properties, it could rupture for a very long way without having too much barrier to that actual rupture. So that seems to fit. That was sort of the explanation for this. Start in a high rigidity patch where you maybe have lots of locking and everything's tight together. It breaks and it propagates through this other region quite freely. We had the exception one here where maybe this is Sumatra, where you have a bunch of these frictionally unstable patches, and if there's enough of a slip or a break on one of those, it can keep triggering the sort of adjacent patches of frictionally unstable material. So that was our little explanation. We submitted a paper to Nature and it never even went to review. And then we made the mistake of saying, let's fix a few things and then do it again. And that was, like I said, 15 years ago. So we've got this observation. The question is, well, what's the explanation for that? And I don't think I have the explanation for that yet. And that's part of what I'm trying to do here. And part of what, sharing this with you is to sort of see if anybody else has got any ideas as well. But, there's any number of things that could cause this. I'm just going to run through a few things that, observations of what's different about the region, like focusing on Japan Trench, what's different about that region that has the low flexural rigidity where the rupture took place, and the regions around it which look to be higher flexural rigidity. Just as sort of a quick validation of those results, I jumped on this little paper from a decade ago where they computed the flexural rigidity or the elastic thickness using plate bending. So rather than this direct correlation in statistical correlations between gravity and topography, they actually apply loads to an elastic plate and bend it. Get matches between the gravity anomalies from that bent plate and what they observe, and see what they can come up with. So they did sort of two scenarios. They just used one model where they had constant elastic thickness across the whole model, and one where they varied it, and they reduced the elastic thickness as you come into the trench, which is something you'd probably expect because it's bending. You get those bending normal faults, which probably weakens the whole system. But to cut a long story short, basically it shows here that north of that rupture zone, the elastic thickness that they found is generally higher, and it's lower in that region adjacent to the rupture zone. And I guess the other point about this is sort of suggesting that those flexural rigidity variations are in the oceanic plate, the incoming plate, because their modelling stopped at the trench, so it didn't look into the sort of the forearc side of things. So okay, that just gives me a bit of validation that those variations we see from that statistical correlation between gravity and topography is maybe on the right track. So what's different? What's different about that? Maybe it's something to do with the hydration of the subducting plate. And a couple of examples here. There's a profile shown here, a seismic velocity model, P-wave velocity model here, and a couple of bits down below show the mantle P-wave velocity perturbation. You can see it drops right off as you come into the trench, and also this VP-VS ratio increases. And that's because the S-wave seismic velocities, which can be really sensitive to the fluids in the crust, that drops off, so that ratio increases a lot. So that sort of suggests that maybe there's some hydration going on in this sort of under the trench, as you get those normal faults potentially going through into the mantle and allowing fluid to come up into the system. Another profile a little bit further to the south here through the sort of the rupture zone. And again, in just looking at one thing here, there's reduced S-wave velocities as you come into the trench. So here's the trench coming in under that system. You've got that reduction as well. So that's maybe suggesting this may be some explanation for this weakening. But if we look at those results compared, they sort of compared that sort of velocity drops to the degree of serpentinization and the amount of water in the system there. And you don't really see any difference between inside that rupture zone and outside the rupture zone. It's sort of 10, 20, maybe 25% serpentinization in the mantle underneath the subducting plate. So that, sounds like a good explanation, but it doesn't really explain that difference. Other things that might come in there is the sediments that are coming in. So we talked about the smectite clays, how important they are. They're pretty weak. Maybe the thickness of the sediments affects things as well. There's just some other results here where they sort of show there are some patches of reduced sediment thickness on the incoming plate, and that's this sort of region here and here. And that's sort of maybe the region where the rupture was blocked. It couldn't propagate any further. And they sort of showed that actually the sediments probably aren't that much thinner. There's actually been intrusions from this petite spot volcanism. So more recent magmatism from little volcanoes, much younger, that have intruded into those sediments and affected the sediments. And in that case, you might metamorphose those weak smectites into illite, and illite is a bit stronger. So, once the rupture reaches those regions, it maybe can't propagate as easily. The sediment thickness variations, there's nothing sort of all that obvious there. This sort of paper showed that the sediment thickness is a little bit less thick, well, it's a bit thinner, let's put it that way, in front of that rupture zone. But that's not really something that's sort of jumping out as particularly obvious why that would change things. In a similar vein, these authors sort of looked at the degree or the amount of normal faulting, that bend faulting on the as it bends into the subduction zone. When I looked at this, maybe in this central segment, which corresponds with this rupture zone, maybe there's slightly more of those normal faults. Maybe that's letting slightly more fluids into the system. But, again, we don't really see that in the seismic velocities, any sort of correlation inside and outside that rupture zone. Of course, it could be the upper plate. It could be the forearc geology. And there's a publication here which sort of looked at residual gravity anomalies, showed they're relatively higher over this rupture zone and relatively lower to the south there, and sort of suggested that this high gravity, residual gravity zone could represent the high density forearc, because that part of the forearc has lots of volcanic and plutonic rocks apparently. And that would suggest you should have higher rigidity here. But our results show that you've got lower rigidity. Similarly, down here, they said the lower residual gravity might be lower density forearc. The rocks there are dominantly accretionary complexes, so lots of stacked up sediments and maybe less strength, so lower rigidity. But again, the flexural, the rigidity results we've got suggest that's coming into a region of high rigidity. So it doesn't really seem to fit either. When we look at the structural style, these are some unpublished results from a PhD student, Aubrey LaPlante in Northern Arizona University. She's been mapping I guess the structural style. This image here is above the rupture zone. You can see it's a little bit more chaotic. Even my daughter Kiara picked up the difference here that there's reds and thrust faults and normal faults. Right across there, it's sort of a bit scattered, but you see quite a demarcation further north. So is that somehow giving us an indication of what's going on the plate interface somehow and explaining this sort of flexural rigidity? Again, don't have the answer yet, but that's just an interesting correlation. And then the significance of this smectite clay again, what's the distribution of that? I'm not sure that that's really been easily mapped yet, but we saw that in the accretionary wedge boreholes and in the incoming plate hole, that 436. And we have those clays again in the new drill site on that incoming site. But again, we don't have all the clay content and everything sort of documented yet. But we do see a similar pelagic clay layer that probably has those smectite clays in it. So the question there is that presence of this smectite ubiquitous? I mentioned before, maybe that volcanism is metamorphosing that smectite a bit. It's confirmed in the site that's in the accretionary prism. We're still to confirm it in the one on the incoming plate, but that will come. And if we look at the some kind of global mapping of the nature of the sediments on the seafloor, this is the results from Adriana Dutkovits, looking at the global compilation of seafloor sediments. And if you look in the region around Japan, there's a lot of this brown color, which is the pelagic clays. So it seems to be reasonably ubiquitous around there. But that's what's on the seafloor, and it's really probably what's happening at a few hundred meters down that's the most important. So then the question would be, does somehow this weak smectite reduce the flexural rigidity, the elastic thickness, essentially by somehow decoupling the overriding and the subducting plates? So if you've got two plates and you put a load on one and they're locked together strongly, they're going to support loads very differently to two that sort of might just slide past each other if you put a load on them. So that's pretty much sort of where it's at. And I don't know if you read the abstract before, you probably sort of saw that I talked about, physical properties. What about physical properties? I haven't mentioned them. And that's partly because I ran out of time. Partly it's because I, went down this little bit of a rabbit hole looking at the incoming plate and what was the nature of that. But, the physical property data of that overriding plate, the accretionary complex, could be something that's going to help us, if that upper plate, that plate above the subducting plate is the key to this whole rigidity. So that's still work to be done. I'll have to come back and talk to you again about that down the track. Hopefully we've found some nice solutions and everything. But in terms of the physical properties, that was my role. We've got the data, and again, it's not quite released yet. So I'm probably not supposed to talk about it anyway. I'll hide behind that excuse again. But longer term, like going back to the start, what I'm really thinking here is, can we somehow use this information from the expedition, these observations with the flexural rigidity, to say something about what's the likely rupture extent when one of these big earthquakes happens? Remembering that the rupture extent constrains the amount of slip, that constrains the seafloor displacement and the size of the tsunami. So is there the possibility to for better forewarning of the most likely tsunami scenario? Is it one where we where we have the very extensive rupture, maybe less slip, maybe a smaller tsunami but more widespread, versus something which has got a lot of slip, a big tsunami over in a more concentrated space? So ultimately the idea is to test this little hypothesis here. So that's pretty much all of the content I wanted to talk about, but I will just share a few of these little personal highlights from this expedition. Things like, it's always good to have a helicopter flight on this classic 40-year-old helicopter. Glad I never got into the rescue boat. We had a look inside, but I really can't imagine life inside them on a rough ocean. Life on Chikyu is really comfortable, even when it's really rough. This engineering, everything that goes into it is just incredible. It's very mesmerizing. You could stand and watch it I could probably for hours, watching this thing just go up and down, slotting things down and threading things down a 7,000 meter pipe, bring it all back up again. Yeah, quite incredible. It was a highlight to be there at for the last IODP core. This is the last IODP core. This is the bottom end of the core liner that last piece of core was collected. So this piece of plastic went down 6,891.5 meters below the sea level, and then another 956 meters below the seafloor. So in there was the last piece of core, and I managed to wangle that one. So precious, don't steal it, please. These amazing chocolate clays, like it really looks like chocolate or fudge or something like that, but I didn't taste it. This is probably a low light. Never got to go to the top of the derrick. Some people did, but whenever I was there, it was always too rough. Would have been amazing to stand 130 meters above the seafloor, rocking around, looking down on the deck below. A lot of the highlights were the outreach side of things. So we had the chance to get involved in a few things. I practiced my German with an outreach event to Germany. I did one with a colleague in Chile with his students. And I think this is a kind of a mind-boggling thing that people can really get excited about and go, wow, this is incredible. There were things like messages to schools in Japan where I told them there's no kangaroos on Chikyu. Claim to fame, I'm the star of a comic, maybe. Am I a superhero now? I don't think so. But there's a great little book of comics that's coming out from the expedition. We will have some copies for that sometime soon. Also a little bit of cultural outreach, managed a few converts to Vegemite. And some who had already been converted and were really happy that I brought some with me. Look, the people, of course, were really amazing. And you can see here, everybody here with the last sort of bunch of cores. So these are all cores from the basalt of the oceanic plate underneath. There's some amazing pillow lavas that we intersected and things like that. But again, can't really talk about them just yet. But I'm going to stop there. And we do have a surprise guest here. Will Grant was out on the expedition for a while as an outreach person. I've just put up a few pictures here, and I was going to give Will a chance just to sort of talk about his experiences and what he made from it. So, yeah, come and stand by the microphone.
As Ron said, I'm Will. I'm from Centre for Public Awareness of Science on the other side of campus. We do science communication work. And I don't want to get in the way of you giving answers to Ron's big question here, because I know he's like, I've talked about this, and you're the brains trust that will help solve this problem. But I travelled on Chikyu at the same time as Ron as part of this expedition, as part of the outreach component. Although I wasn't doing formal outreach in terms of science communication. Instead, I was looking at how the scientists on board the Chikyu, aboard the expedition, think about and talk about their work to other people. What is the meaning of their work? What are they trying to achieve? And it was just great seeing in Ron's work just there, thinking, okay, so what is the ultimate goal? That as we learn more about this, the slip zone, how might then that modeling allow us, or more accurately, people in Japan, to model what the impact of a potential tsunami or potential earthquakes might be? Because our goal really is to do science that tells us about the universe, but also that gives us options as societies around the world to mitigate the worst of disasters or to understand what we might do as societies going forward. I just wanted to flag that we're so grateful. One of our PhD students is traveling on I don't know if it's the next one or the one after in October, to go and as part of the outreach crew as well. And we're really keen to support and be part of this because we know that Earth science is doing great things to understand more about our planet, and collaborating with other disciplines, other areas, is ways that we can not only understand, but also reduce some of the risks and dangers. But anyway, back to Ron. Thank you, Ron.
Thanks, Will. Yeah, so Sarah, right? It's Sarah Barnes.
Yes.
Yeah. So Sarah's going on. There's another Chiku expedition starting in about a month, just a short one, 3 or 4 weeks. And they're actually going to drill, that expedition's going to drill into one of these petite spot volcanoes to try and understand them a little bit more. And Andrew Roberts has actually got a place on that expedition to go and do some more paleomag there as well. And then there's another expedition right after that one, which is going back into the Japan Trench and doing some drilling in the actual trench sediments, trying to look for the tsunami records back, I can't remember how far, thousands of years, because there was an expedition a couple of years ago where they used giant piston coring at, I think, 15 or 20 sites along the trench, trying to get that tsunami record along the trench. So there's one site where they're going to go back and try and drill and get that record a little bit deeper. Whole lot of stuff happening there in the Japan Trench. So look, I think that's pretty much it. Yeah, so it was a grand finale. It was a grand first for me, probably a one and only, I would imagine. But hopefully it's going to be an opportunity to sort of test that hypothesis that's been sitting in my brain for 15 years. And if I achieve nothing else before I retire, then hopefully I can come up with something on that. Yeah, like I said, welcome your questions, welcome your ideas. And yeah, we've got Chiku here, and you can have a look at the four-liner as well. So thanks for coming along. Thanks for signing in if you're online.
Thanks so much, Ron. Do we have questions for Ron?
Thanks, Ron. That was super interesting. I just wanted to clarify about in your results, the flexural rigidity. The flexural rigidity of what, essentially? The incoming plate, the overriding plate, both, or you don't know? Or...
It would have to be both. Yeah, it'll be, because it's the gravity signal's got everything in it, and the topography reflects all those processes together. So it would be both. At some point I was thinking, okay, maybe it's the stuff in the overriding plate that's somehow affecting that flexural rigidity, because you see that change in structural style. But then, a week or so ago, as I started putting this together, I started going down that rabbit hole, and okay, well, maybe it's all in the oceanic plate. Which, when you think of bend folding and all that, faulting and all that kind of thing, it's, that should be an obvious way you would affect the flexural rigidity of the incoming plate, and maybe the overriding plate is a small part of that. But maybe it also affects, it's affected by the degree of coupling between that overriding and subducting plate. And again, like I said, there's all these things bouncing around in my head, and I don't know which one. But yes, it would be both when you come onto that into the fore part of the system.
You can't along from variation gravity signal, I guess.
Gravity and topography, yeah, and this. No, it's reasonably consistent, but again, that gravity map that I showed towards the end of one of those examples, that's a residual gravity image. Can I get to it quickly? This one. So this one here is a residual gravity image. So it's sort of an average profile along the trench there is subtracted. So you do see some subtle variations, and you would see those sort of variations in residual bathymetry as well, which these people also computed. Yeah, so there are some variations there that somehow reflect it. And yeah, I don't know. I think, when it comes to subduction zone, there's so many variables. I don't think anyone's quite nailed it yet about what's the dominant control. Maybe it's different for everyone. Is there another?
Hi. Sorry, there were two questions. I have lots of questions, but unfortunately, one of them is more kind of fun. So, in terms of the practicalities, first boy is called Derek. And when you said you hit the chute, what do you actually do in that scenario? Do you move the boat and drill elsewhere, or how do you actually get around that? I have a serious question after.
Yeah, okay. The Derek question, I don't know. Does anyone know? Sarah would know, but Sarah's not here, unfortunately. Yeah, I'm sure that's where it would have started, but I don't know why Derek in particular. But yeah, there's some homework. Well,
Yeah, I think I've never heard it called Derek.
what have you heard it called? So I don't know if anyone's listening online and can put it in the chat or something. Yeah, but I'm sure that's that solution. Thanks, Will. That solution is that's an easy answer to find. The drilling through chert, but basically that chert is pretty ubiquitous everywhere because it's a characteristic, from it forms at the time of, early on in the plate's evolution. So that chert is everywhere. So whatever happened, you had to get through the chert. Yeah. And it wasn't really a case of saying, okay, we'll move somewhere else and see if it's not there. We knew it was going to be there. So the logistics of that is, okay, well, we're trying, we're not getting through. So then that drill bit, had the hole in the middle. They actually put they call it a center bit. So they blocked the hole. Said, okay, well, maybe that'll help us get through, but that still kept wearing down. And at the time they were trying to core, they said, okay, we're just going to have to bring everything up, check the drill bit, then they had to change the drill bit and put it all down again. And then we're just going to drill through the chert without taking any samples. And then you can optimize things a bit better if you're not trying to take core. You can use a slightly different drill bit, that kind of thing. And then when we're through the chert, bring everything back up again, 40 hours, put it all down again with the coring bit, 40 hours, and then drill again. And then that's when you get into the basalt, and the basalt's much easier to drill in. So yeah, really it's just trying lots of things. The drilling engineers have all sorts of things they try as well. Do you change the rate of the drill bit turning? Do you put more weight on it? But you can't put too much weight on it because you'll bend the string. It's quite amazing. And I think part of the fascination of this, for me, it was really interesting because I wasn't in charge of that expedition, but watching there were 6 co-chiefs, 3 of them there at a time. They're presented kind of with 5 or 6 different options, and they'll never know what 5 of those 6 options would have resulted in. That's making that decision at the time about how we're going to get through the chert. Yeah, obviously we did. On the incoming plate where we were supposed to get into the basalts as well, we didn't because we ran out of time to go back and, because of the problems getting through the chert on the main site. It was okay, well, let's not even try out there because it's going to take too long and we'll probably lose another drill bit and all of that kind of thing. Yeah. Penny? So the Derek refers to the gallows, the surname of a London hangman. Okay, okay.
Does that change your opinion of it?
Should we call it something else?
It seems that this is really tricky because if it's a rigidity thing, it's really quite large scale, kilometers.
Yep. And long term as well.
Whereas what I'm seeing is slip on the slip diagram is making chocolate color, which is actually quite local and could be water coming and going in cement ore. So that's a local thing. So how do you decide on your scaling of what's going on? I don't know that this adds up.
Yep.
It's like, is there a way to do that? Localized scaling versus.
So I'll just sort of repeat that, Sammy, in case people online can't hear it as clearly. But the question from Penny is about the scale. So we've got that large scale flexural rigidity, which is lithospheric scale, loads, big mountains, subducting plates, pulling down, all that kind of thing, versus that very short time scale of the earthquake slip, which is okay. Yeah. So I think it's one of those cases of big influencing small and small influencing big, maybe, in a way. So I'm thinking on the fly here, but you can have these very big systems, but it could be one little thing. And I think that's what's been surprising about this fault zone as well, is it is so narrow, and the slip has probably been accommodated on something, maybe even a centimetre thick, with all of that stuff on top of all of that stuff on the bottom. So you can have a situation where at that small length scale, you can have properties that are so stark that they can affect things on that bigger scale, or not be affected by the things on that bigger scale. I don't know, is that sort of answering your question, or does anyone else want to have a go? Yeah. Yeah, that's right. Yeah, and maybe it's a little bit like the the air hockey puck or the ice hockey puck or something. It's sliding very easily when normally it would just be heavy and should sit still. Yeah, I see Mark sort of gesturing a little bit there, but oh, you got a question? So does that? Yeah, let's talk about that one more. Yeah, but I think it's to me it's one of those things that you can. It's quite incredible that such a minor thing can seem to have such a big influence when you think there's all these other things happening on top of it. And but it's all if it's a local scale thing over a long term. So because it's gravity, the gravity means it has to be a long term thing, because gravity doesn't change that fast. Geology doesn't. The shape of the forearc and thing doesn't change. So if it's had that characteristic for a long time as well, then it could still be okay there. Yeah, I mean, the other thing that I didn't say here as well, like I said, there were those 11 different drill holes. There were a couple of drill holes through that fault zone, and there were places within 20 or 30 meters of each other where the stratigraphy was completely different. So that that pelagic clay layer was almost completely gone, and in places it was 20 meters thick, over really, really small distances. So yeah, the change is quite incredible. Yeah.
Last question from Mark.
Yeah, thanks on that. But just because you don't understand it doesn't necessarily mean it's not useful for the reason you motivate this whole thing. Have you looked at where there are other patches and started to identify from a fault hazard perspective where else might be a problem?
So I guess I haven't looked in any detail other than this Japan one, like in recent time. Back in when the Chilean margin was probably the one which we thought about the most, and I didn't. Can I find that quickly? The Chilean margin, that rupture zone seems to correspond with the sediment thickness. So what's also shown on this plot is these contours of sediment thickness. And sort of where those sediments run out, that rupture doesn't necessarily sort of propagate. So when we were first looking, we were thinking, okay, is it something to do with the sediments that are filling the trench? And in this case, in Chile, the sediments are very, very thick, so they're producing a nice smooth interface, which is probably somehow facilitating that conditional stability that you've got a nice smooth interface. It'll slip reasonably freely unless something triggers it to go fast, maybe. But so sediment thickness could be something as well. There's any number of things. So no, we haven't looked at the rest in detail. So in this case, because I was on that expedition, I've got to write something about Japan. I'll start there. But then, like I said a minute ago, you can think you've got it worked out in one subduction zone, and then you go to the other ones and it's completely different. There was a paper published earlier this year by Dan Bassett and some others where they sort of said, okay, we've picked out some things we think are the common things, but that's only for 3 subduction zones as well. So Hikurangi and Nankai in Japan, and I can't remember where the other one was. But I suspect if you looked at those parameters in a different one, it'd be something different again. But yeah, you're right. I mean, that's your first part of that question was, we have the observation that something seems to work, and if that somehow helps you map out what the tsunami's doing, then yeah, it could be useful. And if I'd said to Dan Jackson, try this, then they might have got something completely different. But yeah, you've really got to have an explanation for it as well, kind of thing.
Great. So today we're going to trial having cake after the seminar. So
Trial.
we could stay. We could maybe continue this into the future as well. Yeah, so please stay around, have tea, and more of a chat with Ron. We had a chat about the announcements this morning, eat some cake, and let's thank Ron again.
Cool.